Welcome back to another video. We are in the middle of our section on Brownian motion, and today there will be another topic called the reflection principle, which means that a Brownian motion can be reflected at a stopping time, and there will be a nice figure where you understand what that means. And a consequence is that we can exactly compute the distribution of the maximum of a Brownian motion up to some time t. So let's see. So the reflection principle. What does it mean to reflect a Brownian motion at a stopping time? Here xt is a path of a Brownian motion simulated in my computer. And t is the random time when it first hits 1. And reflection means, well, initially the two things are the same, but after the stopping time, I just mirror the path at x equals 1. So this here is just reflected. And the claim is that this reflected path here is again a Brownian motion. It's not that surprising. So again, if t would be a fixed time, it's clear that it's also Brownian motion because the increments of Brownian motion have a symmetric distribution. But here t is a stopping time, so it's not that clear anymore, but still it holds. And just for the formulas here, so this reflected Brownian motion, well, xt before time capital T, xt prime equals xt, and afterwards, well, I write here something like x capital T, which is where it just is, plus, so the non-reflected would be minus, the non-reflected would be plus the increment, which is xt minus x capital T. And now I reflect this, which means this here is a minus. And when you do the algebra, well, that's just 2x capital T minus xt. So that's the same as here. Let's prove this, that this here is also Brownian motion. And the proof is not long. It uses much of the independence which we know that we have in a Brownian motion. So yt here is the Brownian motion stopped by time t. And zt, well, it's the increment starting at time capital T. And another thing which we will need is z capital T. There I shift time by capital T. So let me try to draw z capital T in this picture here. So z capital T in this picture would stay at 0. Because up to time t that I have just 0 here. And setting 0 is 0. And then it makes the same as x. Well, so it follows parallel to this path here. So let me try to draw this. So that is my z capital T. And y, okay, y is the same as x until here, and then just stays. So this here is my yt. The idea being that yt plus z capital T is xt, as you can see here. And yt minus zt is the xt prime. And I have to show that yt plus and minus zt has the same distribution. And the argument is that t, y, and z. So they're not independent, but ty and z, they are independent because of the strong Markov property. So z is the increment after the stopping time. We know Brownian motion is a strong Markov process, so that's independent of what came before. So ty and z are independent. And z and minus z has the same distribution because increments, well, have symmetric distributions. So these here have the same distribution. I can ignore the t, of course, in this joint distribution. So y and zt and y and minus zt have the same distribution. Yeah, because this here is just a function of t, y, and z, and the same function of t, y, minus z. Well, and if this here is true, then y plus this thing has the same distribution as y plus this thing, which amounts to x and x prime having the same distribution. Okay, that's the reflection principle. So Brownian motion reflected at a stopping time is again a Brownian motion. And we are using this on this slide here, sorry, it's a little bit full here, to see the following. So mt, that's what I said in the intro, that's the supremum of xs as less or equal than t. So let me just delete everything which I drew here. So mt, let me draw the screen. That's the maximum process. So here, well, that's the maximum. It's the maximum. Maybe like this here. And from here on, the Brownian motion is not above this thing here. So this here is the maximum process of Brownian motion, xt. It's not the maximum process of xt prime. It has the same distribution. Well, that's a different story. We want to compute the distribution of the maximum. And the claim is that this maximum here has the same distribution as the absolute value of xt. Well, the absolute value of xt, this distribution, let's just mirror this path here. So at 0, so everything which is underneath to below, to above 0, and that's the absolute value of xt. And the claim is these two things have the same distribution, which is a bit crazy because mt has completely different paths than the absolute value of xt. So how can we show this? And there's a second claim actually, that also mt minus xt, which is the distance of mt and xt, so that's this distance here, that has the same distribution again as mt and as the absolute value of xt. So tx is the first time Brownian motion hits x. And xt prime is a Brownian motion mirrored, so reflected, I should say reflected at time t, and y is less than or equal to x. And the reflection principle allows for this equation here to hold. Here, let me draw a picture. I have an x here and I have a y here. And the event that I'm calculating here is the maximum by time t is bigger than x, but xt is smaller than y. So the path must be something like, well, it hits something above x and then drops below y. That's the kind of path that I'm looking at. Since mt is bigger or equal than x, this stopping time tx has to have occurred before time t. Has to have, it has to have happened here. Which means I can use the reflection principle and reflect the path here, such that I'm looking at this path here. And what did this path do? Well, first of all, it's again a Brownian motion, as we know from the reflection principle. So here it grew until x, and it did not drop below y, but it is above x plus x minus y. So 2x minus y. So it's above this thing here. Because if it's above here, okay, then it's also the maximum is above here. So the reflection principle is responsible for this equality. Well, and how do you compute this? Let's say phi t is the density of xt by time, so of x by time t. So the density of the absolute value of xt, so what can happen in absolute value of xt? I have phi t of x, only if x is positive, but 2 times because of the absolute value, because there are 2 possibilities. Xt is either above x or below minus x, so to speak. So this here is the density of the absolute value. And our task is to compute that mt has the same density, so this density here. Okay, but phi t is the density of xt, so when I want to compute this thing here, well, I integrate from 2x minus y to infinity over the density. Okay, that's as usual. But from this, I can say, well, mt is bigger or equal than x. How can this arise? Well, okay, this equality only holds for y less than or equal than x. So I can distinguish this thing here into 2 cases. Either mt is bigger than or equal than s and xt is smaller or equal than x. Or the same thing holds and xt is bigger or equal than x, but if xt is bigger than x, then mt is of course also bigger than x, such that I can forget about the mt portion in the second bracket here. What's the probability that xt is bigger than x? Well, that's this integral, of course. And for the other thing, we can use this integral with y equals x, which is the same integral from x to infinity, phi t of z dz. So I have twice this integral here, and therefore we have computed the distribution of mt, which is the same distribution of this absolute value of xt. So that's the first claim. For the second claim, we have mt minus xt. Well, how can that arise? So how does mt minus xt arise? And here I just wrote it down a bit more complex. So mt is something. So mt is some between z and z plus epsilon for some z, which I integrate over. But if mt is z, then xt has to be smaller than z minus x. So like this in here. And the plus epsilon here, I just use, so epsilon is small, such that mt is close to z. But when I write it like this, I can also write it like this. So mt is bigger than z, minus mt is bigger than z plus epsilon. Like so. And now, again, I can use this equality, what we had before. We only have to be careful because here is a z where he's an x, and here's a z minus x where here's a y. And the lower bound here is twice x minus y. So I have here twice z minus z minus x, so z plus x. So that's this thing here. And similarly, I have twice z plus epsilon minus z plus x. So I have z plus x plus 2 epsilon phi t over pi dy. And again, I'm integrating all this over dz. But now, well, okay, what's this difference here? That's the difference. I'm integrating from z plus x to z plus x plus 2 epsilon. And I integrate 1 over epsilon here. I have 1 over epsilon here. And what remains here is phi t of z plus x. So I can delete this. I can delete the whole bracket and write phi t of z plus x. Wait, 2 times, and the reason for the 2 times is that I have a 2 here, but only 1 epsilon here, so would have to write a 2 here and a 2 here, and the 1, 2 stays, which is this one here, like this. And the integral from 0 to infinity 2 phi t of z plus x, I can also write, well, using some transformation, I start from x to infinity and integrate 2 times phi of z dz. And again, this here, and I forgot a t. And again here, that's the same density as the density of absolute value of xt and of mt, which means also mt minus xt has the same distribution. Okay, that was it for today, and more on Brownian motion in the next video. See you then.